Electrostatic potential and capacitance. Potential and potential energy. To discuss details of electrostatic potential and potential energy, let us remember what you have learned about gravitational potential and potential energy. Now, the body of mass m is on the ground. It cannot move by itself in the upward direction. To lift it upward, external work is done against the gravitational pull of the earth. Let the mass m is lifted upward with an external force to a height h. The external work done is F into S, that is mgh. External work done on this mass m to lift a height h is stored as its potential energy. When the external force is removed, the body moves, gaining kinetic energy and losing an equal amount of potential energy. When it reaches the ground, its potential energy becomes zero. Here, the potential energy is gravitational potential energy. The same way, we can find the potential and potential energy in an electrostatic field. Same as gravitational field around a mass, there is electrostatic field around a charge. If a charge of same type enters this field, it experiences a repulsive force and moves away in that field. Consider a charge Q which is placed at the origin, and E is the electric field around this charge. Let us imagine we bring a test charge Q from a point B to a point A. Here you know there is a repulsive force acting on this charge Q. So we have to do external work done to bring it from B to A. To move the charge from B to A, we apply an external force E external just enough to counter the repulsive electric force Fe. Work done by the external force is in the opposite direction of the electric force, and it is fully stored in the form of potential energy of the charge. If the external force is removed, when it reaches at A, the electric force will take the charge away from Q, and the stored potential energy is used to provide kinetic energy to the charge Q in such a way that the sum of the kinetic and potential energies is conserved. As work done by external force in moving the charge Q from B to A is WBA is equal to integral B to A Fe dot dl. The direction of F is shown here. Similarly, direction dr is also shown. Therefore, WBA is equal to minus integral B to A Fe dl. This work done is against electrostatic repulsive force and gets stored as potential energy. Test charges at different positions in the electric field it possesses certain amount of potential energy. When it is at A and when it is at B, the potential energy is different. The difference in potential energy between A and B is delta U is equal to potential energy at A minus potential energy at B. That is equal to the work done in bringing this discharge from B to A. Or we can define electric potential energy difference between 2 points as the work required to be done by an external force in moving a charge Q from one point to another in an electric field without any acceleration. Point B is at infinity. The potential energy of the charge at that point B when it is at infinity is 0. Suppose you are bringing the charge from that point to A. The potential energy of Q at a point can be defined as the work done by an external force in bringing the charge Q from infinity to that point. Potential at a point in an electric field can be defined as the work done by an external force in bringing unit charge from infinity to that point. The difference between the points A and B is defined as the work done in bringing a unit positive charge from B to A. V is the potential difference between the points A and B. That is VA minus VB. The potential at A and potential at B are different. At A, the potential is higher than at B. More work is required to bring the charge from infinity to A because A is near to charge Q. Let us distinguish potential at a point and potential energy at a point. Potential at a point is the work done in bringing a unit charge from infinity to that point. Potential is represented by the letter V. Potential energy at a point is defined as work done in bringing a charge from infinity to that point. Potential energy is represented by the letter U. The relation between potential energy and potential is U is equal to QV. Potential is a scalar quantity and it is represented by the letter V. Potential energy is also a scalar quantity. It is represented by the letter U. Potential means the energy possessed by a unit charge in an electric field. Potential energy means the energy possessed by a charge in an electric field. So there is a relationship between potential and potential energy. That is, potential energy of a charge Q in an electric field is given by U is equal to QV.